Hello, welcome to the third mini lecture on Laplace transforms. This is another revision lecture. The first two looked at the definition of the Laplace transform and lots of examples. This one's going to look at how to do the inverse Laplace transform, and it's going to do it not by using the definition that we saw earlier in the first lecture with the integral form, but instead we want to try and convert our functions into simpler versions that we can convert by inspection using the readily available tables. That will make our lives a lot easier, and you can solve all the problems you need doing that. So it's partial fraction expansions. You'll have done this before in maths and elsewhere, so this is a revision of this method. Remember that our Laplace transforms looked like this. They were x of s was a polynomial qs divided by another polynomial ps. There are three steps to what we're doing in this lecture. The first one is to do the partial fraction expansion. That will turn this expression into this expression. Whatever the order of the polynomial p is, we'll have that many terms here. And we are creating these to be low order polynomials. Low order polynomials means we're likely to find what they are in the Laplace transform tables. Once we've got the right form of the solution, we need to compute our individual coefficients, c1 to cn. And then finally, it's the easy bit, the actual inversion. And we take advantage of the linearity of Laplace transforms. So our function here, which is the sum of lots of terms, can then be separated out into the sum of lots of inverse Laplace transforms. So long as we can find an expression that looks like this in one of the tables, then we'll be able to write down what the solution is. This is a copy of the University of Manchester mathematical formula tables, and you'll have seen this in exams in previous years. It contains lots of useful information about Laplace transforms. So it has the definition of a Laplace transform, and it has lots of examples where it shows the function in time and the transformed function in S. So long as we can use the partial fraction expansion to get terms that look like these terms, as we work down the table column, if they look like that, then we know that we can do the inversion very simply. So that's the objective. There's lots of useful information in these tables. Derivatives and integrals, time delays. It's all in here, so get familiar with them for exams in future years. So I said there were three steps. The first step is to find the roots of the polynomial ps. This is going to enable us to split it up into the partial fraction expansion. Now what I'm talking about today is to do with proper rational expressions. So that means that the order of ps on the bottom of the fraction is greater than the order of qs on the top. If that's not the case, then you'll have to spend a moment thinking about how to tackle that, and you can find that out through other resources. So there's an example of a proper one. That's order 3 and that's order 1. If it looks like that, it will work out. If it looks like this, x squared minus 1 is order 2, and this is an order 1. If your expression looks like that, it won't work straight away. You'll have to do a little bit of work to convert that into something that we can use. Okay. Next, you want to find the roots of this function. That means find the values of s where the function is equal to 0. Now, I trust that you can do that by inspection or by some other means. I won't cover that here. But we will look at two cases where the polynomial ps, it either has n distinct roots, they could be real or they could be complex, and the other case is that ps has multiple, i.e. repeated roots. So that's to say it has more than one of a particular value for its root. And we need to treat those slightly differently in our method. First, we'll look at this one. Distinct real roots. So the second step is to compute the constants. So this is an example which we will use to illustrate the process. Polynomial order 2, polynomial PS, which is order 3. So we've identified that that's the polynomial PS there, s cubed minus 2s squared minus s plus 2. You'll be able to see for yourself that this has roots p1 equals 1, p2 equals minus 1, and p3 equals 2. If you plug those in, you'll find that ps equals 0 for those three cases. And that enables us to do the partial expansion. There we go. The partial expansion starts by saying that we can write our polynomial s cubed minus 2s squared minus s plus 2. We can write that as this function s minus 1 multiplied by s plus 1 multiplied by s minus 2. Because we know the roots, each of these terms can be found, so s minus 1 must be a term because we know that 1 is a root. So when s is equal to 1, s minus 1 equals 0, and so the function is equal to 0. Likewise here, when s is minus 1, the function must be 0, so if s is minus 1 plus 1 is 0. So this will make the function 0. So this form of expansion will satisfy making PS the same as what it was before. Now we can turn that into the partial fraction expansion. We've got something on top, QS, and we've got our expression for PS on the bottom. The partial fraction expansion tells us that we can split it up into each of these terms, each with a different coefficient on top. Now this is the attractive thing, is that as soon as we get to that point, we can see already what the solution is going to look like. Even though we don't know what C1, C2 and C3 are, we can see that the form of the function of s, and we can start to use tables to find out what this looks like. So using the tables, a 1 over s minus a type expression goes to e to the at, and so here we have c1 e to the t plus, again the same sort of expression, plus c2 e to the minus t plus c3 e to the 2t. So we're jumping ahead to step 3 when we do that. We don't know the solution yet because we don't know c1, c2 and c3, but we can see what the general form of the solution is going to look like. So what we need to find is the particular solution, which is defined by then c1, c2 and c3. There it is again. How do we find c1, 2 and 3? Well, here's the trick. A little bit of neat algebra helps us to identify what they are. So this is the method that works for the case where you have different roots for each one. We want to find coefficient c1. So we note that c1 divided by s minus 1. So we multiply the left and the right, all of it, by this term here, s minus 1. So here we go, we've multiplied it here, s minus 1, and we've put s minus 1 on top of each of these. Now, when we do that, you can see immediately this can be simplified. We can simplify this side by dividing 3 by s minus 1. Again here, divide 3 by s minus 1. Now you notice these two terms have an s minus 1 on top. So this expression is true for all s, and so s can be any value that we want it to be. So what we want to do is we want to set s minus 1 equal to 0. This has the effect, this is the trick. If s minus 1 is 0 here and here, that will eliminate C2 and C3. So we can get rid of two of the unknowns and we're left with one equation with one unknown, C1. So we're eliminating the unknowns by judicial selection of a value for s. So if s minus 1 is equal to 0, that means s is equal to 1. We plug that into the equation, and then we're left with C1 equals s squared minus s minus 6 divided by s plus 1 multiplied by s minus 2. Okay, that's straightforward here. S is equal to 1, and so we work that through and find that C1 is equal to 3. So careful selection of the form of the equation and then the value of s enables us to eliminate the some of the unknown coefficients, and then we can work out the one that we want. So we can do the same thing sequentially for each coefficient. When we want to find the coefficient C2, we multiply both sides by s minus 1. So that's the denominator of the fraction associated with C2. And then again, we use the special case where s plus 1 is equal to 0, i.e. s is equal to minus 1. We substitute in that value, that particular value of s, and that will enable us to eliminate some of the unknown constants. So we can see we've done that here. We've multiplied by s plus 1, s plus 1, s plus 1 and s plus 1. Again, there's some simplification. We can remove those and eliminate those. So again, when we now set s plus 1 equals 0, this term is 0, this term is 0, and we're left with an expression just for C2. So we write that out, we substitute in our particular value of s equals minus 1, and here we find that C2 is equal to minus 2/3. So this is such a simple method that works very nicely for this case where you have all different roots. Exactly the same for the third coefficient, C3. Now we multiply through by s minus 2, i.e. s equals 2 for the special case. We see it again here, so again cancel out those terms. We set s equals 2 so that this is 0 and this is 0, leaving just coefficient C3. Again, we can then work out what the coefficient C3 is. It's minus 4/3. At that point, we've done the partial fraction expansion. We've calculated the individual coefficients, so we're ready to actually find our solution. So write out in full what the Laplace transform is after the partial fraction expansion. 3 divided by s minus 1 minus 2/3 1 divided by s plus 1 minus 4/3 1 divided by s minus 2. And now it's in that form, we can do the inverse Laplace transform, take advantage of the linearity of it to separate them out and take out the coefficients. And so now we're looking for the inverse Laplace transform of 1 divided by s minus 1. And we saw that already in one of the examples. We saw that 1 divided by s minus a is equal to e. The Laplace transform inversion is equal to e to the at. They're all of the same form, it's just the value of a that changes in each of them. And so here we are with our final answer in time, 3e to the t minus 2/3 e to the minus t minus 4/3 e to the 2t. That's fantastic. So we've got now the response of a system perhaps in the time domain, so we can see what actually happens. And we've done that, we've solved those differential equations by using the Laplace transforms in a very simple algebraic way with some neat rules. And this works too for the complex roots. I said in the last lecture that one of the reasons we use Laplace transforms is that they can cope with both transient decays and also with frequency responses, and so the complex roots you'll see are going to tell us about that. So now we've got a different example which will illustrate what happens. S plus 1 divided by s squared minus 2s plus 5. This has two roots. They're different roots, 1 plus 2j and 1 minus 2j. So this is complex conjugates. We can see that our function ps s squared minus 2s plus 5 comes out of this, and we can use the roots here to expand that. S minus 1 plus 2j multiplied by s plus 1 minus 2j. Put that in as the denominator of our fraction, and then we can do the expansion into the two terms with coefficients c1 and c2. Again, we can jump ahead and think about step 3. Even though we don't know what c1 and c2 are, we can see that this is the general form of the solution that we're going to get, because we've got recognizable terms here and here. It doesn't matter that these are complex numbers, it's still a number that can be used as a in the Laplace transform inversion. So I said that the same method works as with distinct real roots when we're doing the distinct complex roots. So define c1. First of all, we multiply by the denominator associated with c1, and then we're going to set this term to be equal to 0, which means s is equal to 1 plus 2j. Here we are doing it. So we've multiplied by this term here, and that's going to eliminate this term here. Likewise, this term here eliminates this term here. And then when we set s is equal to 1 plus 2j, this term here is going to go to 0. So we're just left with an expression for c1. So we can write that out again. When s is equal to 1 plus 2j, we have an expression for c1, which is this, when s is equal to 1 plus 2j. Plug in a value for the value for s. So s is 1 plus 2j plus 1, s is 1 plus 2j minus 1 plus 2j, minus and minus makes a plus 2, plus 2j. So you can see that can be simplified. We've got 1 plus 1 is 2, and then we've got 2j, so take that out as a factor, 2 times 1 plus j, and down here we've got 1 minus 1, so that cancels each other out. 2 plus 2j is 4j. Let's make that simpler, get rid of the complex bit on the bottom. So multiply with the top and bottom by minus j, so j times minus j equals 1. And we can simplify our answer to 1 minus j divided by 2. So this works just fine for the complex roots as well. Likewise for the second coefficient, c2, same thing, multiply by the associated denominator and set s is equal to 1 minus 2j. Same process will give us our value for c2, 1 plus j divided by 2. We're ready to do step 3 to find the inverse Laplace transform. So we'd already seen the general form of it, and now we can put in our values for c1 and c2. And there we go. What does that look like? Well, not so clear maybe at first inspection, But we know when we see things like this, e to the jt term, we know that that's an expression of sinusoidal functions. And so we're thinking we can simplify or convert this way of writing it into one with sines and coses, and things like that, which you might find more intuitive to look at. So first step is to just group together the complex terms. So we can take out the term e to the t. So e to the 1 times t is there, and e to the 1 times t is there. So we take that out, and we take out the divided by 2 as well, and we're left with these two bits here. So let's try and convert those into something more friendly. We have Euler's identity. This is showing how the representation of a complex number of e to the j alpha is equal to cos alpha plus j sine alpha. And so our terms are e to the 2jt, so we can write this out as ours look, e to the 2jt, cos 2t plus j sine 2t. So we're just substituting in for alpha. Likewise, e to the minus 2jt, this term here, substituting alpha is equal to minus 2t, and so we have cos minus 2t plus j sine minus 2t, and then we know that cos of minus 2t is equal to cos of 2t, and we know that sine of minus 2t is equal to minus sine 2t. So now we've simplified these expressions. Substitute those into our solution. It gets a bit lengthy, but it's perfectly simple. So e to the t divided by 2, 1 minus j times this term, which is our substitution for e 2jt, plus 1 plus j multiplied by this term, and this term is here. That's our substitution for e to the power minus 2jt. Now this looks like something that can be simplified. We've got a 1 times j sine 2t. Here we've got a 1 times minus j sine 2t. So we can see there are some terms that are going to cancel out. You can do that yourself, and you'll find that this simplifies to e to the power t cos 2t plus sine 2t. That's great. So this is something that's much more familiar looking perhaps to you already, and shows, like what we said, is that the Laplace transform is perfectly able to tell us about the frequency response of a system, as well as its transient response. We can actually do a little bit more to simplify this. Remember this identity, a1 cos b plus a2 sine b equals the root of a1 squared plus a2 squared multiplied by sine of b plus phi, where phi is tan inverse of a1 over a2. Implement that. We see that phi is equal to inverse tan of 1 divided by 1, which is pi over 4, or 45 degrees. And when we implement it, then we get our solution is e to the power t times root 2 times sine b plus pi over 4. And of course b is 2t. So that would be our final solution. And that's nice because rather than just having the cos plus sine type term, now we can actually see what this will look like. It's going to be a sinusoidal function with a phase shift, and it's exponentially increasing. The magnitude of the oscillation is exponentially increasing with time. So that's great. So we've done two cases where we have distinct roots, and we've shown that we can do it for real roots and the complex conjugate roots. So the other case to look at then is where we have multiple roots. Do that sequentially. Where we have multiple roots. So the first step was the same, and we found what the roots of our equation are. There we go, I missed a bit. So again, we'll illustrate it by example. Our Laplace transform function is 1 divided by s plus 1 cubed multiplied by s plus 2. And this cubed function means that obviously s equals minus 1 will be a root, and the cubed means that we have that root 3 times. And then our fourth root is s equals minus 2. That's our fourth root. So that's what we mean by multiple roots, and so when we've got these terms like that on the bottom, that's when they're going to be occurring. The expansion works okay. We do it in this form now, where we expand c1 over s plus 1 plus c2 over s plus 1 squared plus c3 over s plus 1 cubed. So with the multiple roots, this term keeps on going up by 1 power each time. And then we have c4 divided by s plus 2. Again, we can jump ahead to see what the form of the solution will look like. This is the general solution of this equation. We can see what it's going to look like. It just then depends on what the coefficients of each of these terms will be, actually what the particular solution is going to be. So how do we go about doing this? Well, there are two things that we can do which are just the same as before. This fourth one here, that's a distinct root, and so the same method we had for the distinct roots before, that will work again. So we can find the distinct root P4 and use the previous method. So you multiply both sides of the equation by s plus 2, set s is equal to minus 2, and then that will deliver the result that c4 is equal to minus 1, and you can check that for yourselves. Now we can focus on this term, the s plus 1 cubed term. So we go to the highest order of the terms representing the multiple root, and the same method will actually work to find this coefficient c3. I'll show you that one. So we've multiplied through by s plus 1 cubed, so we've multiplied by s plus 1 cubed here, and that's eliminated that one, so we have 1 over s plus 2. We've multiplied by s plus 1 cubed here, so it's divided by s plus 1, and so it becomes s plus 1 squared. Likewise, this is s plus 1. c3 simply becomes c3 on its own, and then c4 has s plus 1 cubed divided by s plus 2. So you can see already that the same method will work. If we set s plus 1 equal to 0, so s is minus 1, this term is 0, this term is 0, and this term is 0, leaving us just c3, and then we can find out what c3 is. We do that, and c3 is equal to 1. So that's great. We've got two of the roots for the same method. But it's not the same for c1 or c2. So let's take an example for c1. If we were multiplying by s plus 1 in an attempt to get c1, we can do that. So we've multiplied left and right sides by s plus 1, so this becomes s plus 1 squared. c1 is on its own, which looks good, but here we've got c2 over s plus 1, here we've got c3 over s plus 1 squared, and here we've got c4 with s plus 1 over s plus 2. And now here's the problem. If you try and use the substitution that s plus 1 equals 0, obviously that doesn't work because this term here will become infinite and this term here will become infinite. So the trick for distinct roots gets us two of them, but it's not going to get us the other two. But it's not too bad. The technique is simply to take this equation. So this is the equation we have after we've multiplied through by the s plus 1 cubed term. We can take this equation and differentiate it. So we differentiate the left-hand side, differentiate the right-hand side. That's a perfectly legitimate thing to do, and we'll find that that helps us. So here we are doing that. This is the left-hand side, this is the right-hand side, and we differentiate both sides with respect to s. The left-hand side becomes minus 1 over s plus 2 squared. This term becomes 2 times s plus 1 c1. This term simply becomes c2. And this term disappears because it's constant, and then c4 requires a bit more work to work out what that differential is. But it will look like that. Already I think you can see that this is an attractive form of the equation because we've isolated c2 on its own, and now we can make the substitution that s equals minus 1 such that s plus 1 is 0. If s plus 1 is 0, we get rid of c1 and we get rid of c4 because s plus 1 is 0. So now the substitution works and we'll get a value for c2. So you put in that substitution and you'd find that c2 is equal to minus 1. Great, we've got 3 of the 4 coefficients. How do we get the last one? Same trick again. Differentiate our expression once more, and that will deliver the next coefficient. So we differentiate the left, 2 over s plus 2 cubed. This term becomes 2c1. c2 is a constant, so that disappears. And now we have this term for c4, which again you can work through to find its differential. Again, this looks good because if we substitute in s plus 1 is 0, c4 is going to be eliminated, c1 is on its own, so that's fine, and this term is going to be okay. So again, we can then make in the substitution that s is minus 1, and then we find that c1 is equal to 1. Fantastic. We've almost finished. The last step is step 3, doing the inversion. And again, that's very simple now because we knew the general form of the solution already, and now we've got our 4 coefficients. We can take a part of the solution outside as a common factor, and so our solution is e to the minus t multiplied by 1 minus t plus half t squared minus e to the power minus 2t. Good. So that finishes our revision. What we've done is we've looked at the definition of a Laplace transform, we've looked at how to find Laplace transforms of simple functions, and we've seen that the Laplace transform can be inverted by partial fraction expansion, and then a couple of different methods for finding the coefficients. And with that, we're going to be able to solve sets of differential equations and in particular understand the transfer function in a control problem, which is what we'll start in the next lecture. Thank you.